Jai Hind everyone. I am Nikita Jaiswal from Civil Engineering Department. I am going to discuss dimension analysis, which is part 2 of my previous lecture on dimension analysis. Now further in this particular lecture, we are going to discuss how we can analyze the dimensions of particular phenomena, fluid flow phenomena by using method Buckingham Pi theorem. So we are introduced to the Buckingham Pi method before. Here we can cumulate all the parameters involved in particular fluid flow problem, and we convert all the parameters in forms of dimensionless quantities, or you can say pi terms. Here we are going to talk about how we can formulate this pi 1, pi 2 or other and pi terms. So there were two methods as we discussed before, that Rayleigh method and Buckingham Pi theorem. Usually we use Rayleigh method when the number of variables involved in particular fluid flow phenomena is in between 1 to 4. But whenever the involved variables are become more than 4, 5, 6 or something related to that numbers, then we can use Buckingham Pi method. So here you can see how we can formulate pi 1, pi 2, pi 3, pi 4. So there are actually some rules. I have taken this screenshot from your book R.K. Bansal, in that particular chapter, even in our analysis, we need to go through how we can check or how we can take repeating variable and non-repeating variables in particular pi terms. So there are certain rules we need to follow that. Okay, the number of repeating variables are equal to the number of fundamental dimension of any particular problem. We know that fundamental variables are actually 3. Okay, mass, length and time, obviously. Now the choice of repeating variable is governed by the following considerations. As point number 1 here is written as far as possible, the dependent variable should not be selected as a repeating variable. Okay, whenever a particular question is asking for a derivation or an expression for a particular parameter, which is obviously will be a dependent variable, so we try to not to take that particular variable as repeating variable. Okay, now the second point is the repeating variable should be chosen in such a way that one variable contains a geometric property, another contain flow property and third contain fluid property. Okay, now in a such a way that the first is geometry, second is flow property and third is fluid property. What are these kinds of property actually? When we talk about geometric, that means it will be simple units of meter, centimeter or mm. So let us suppose you take any geometric property, so that can be length, that can be diameter, that can be height or head. Okay. The next is flow property. What will be the flow properties? What? Flow property of flowing fluid, obviously. If particular fluid is flowing, what are the associate properties with that particular flow? Can be velocity, can be acceleration. Okay. Now variables, there are different kinds of variables that are associated with fluid property. Okay, that may be viscosity, dynamic viscosity, kinematic viscosity, even mass density or weight density. So here mu is dynamic viscosity, rho is your mass per meter cube, and here is specific weight rho g. So this kind of variables are actually variables related to fluid property. Okay. So here we can take repeating variables in this particular manner. Now the repeating variable should be selected not form a dimensionless group. Okay, the repeating variable selected should not form a dimensionless group. Obviously, the repeating variable together must have the same number of fundamental dimensions. Okay, This is obvious. We are going to solve for LHS and RHS. We should have a same number of fundamental dimensions. No two repeating variables should have the same dimensions. Okay. In the most of the fluid mechanics problem, the choice of the repeating variables may be, the first is, you can see here, diameter, viscosity and mass. The second is length, viscosity, mass. So there are certain ways. See, when I am solving a particular problem, it may happen that I take repeating variable in some other choices or some other serial number. Another one who is solving, or my student, some of my student is solving that particular question, he can take the repeating variable in other manner. Okay. So whatever manner we are taking the repeating variable, non-repeating variable, a little bit of final equation may get vary, but all over when we derive again, we'll get the same equation, or almost 99% same equation. So we are going dimensional this analysis, Buckingham Pi theorem. We are going to understand it, or we are going to solve it by taking a proper example. Okay. Here is question number problem number 12.8. Again, I have taken this particular question from your book R.K. Bansal. Okay. The first question is state Buckingham Pi theorem. You know very well how you are going to state this particular Pi theorem. Okay. Second question is our numerical, which is saying the efficiency eta of a fan depends on the density, okay, dynamic viscosity, angular viscosity and diameter of the rotor and the discharge. Okay. So the dependent variable here is eta, independent variable is rho, mu, angular velocity or omega, diameter and rotor discharge. Okay. So the number of variables involved in this particular phenomena is what you can say 1, 2, 3, 4, 5 and 6. Now the question is asking express eta in the terms of dimensionless parameters. Whenever you got confused what kind of method you can apply, just count the number of variables involved. It is more than 3, then go for Buckingham Pi theorem, or directly that particular question may ask you, you can apply that particular method. So just we can go through the solution, that eta is a function of rho, mu, omega, d and theta. So how you are going to write an equation like this? Eta is function of rho, mu, omega, d and q. Okay. Or you can write it as function of 1 is of eta, rho, mu, omega, d and q. Okay. You can write it as like this. So just count it, count the values, count the variables 1, 2, 3, 4, 5, 6. So here you can say n is equal to 6. And what is our m? Fundamental dimensions is equal to 3. Okay. So when m is 3 and n is equal to 6, and also you need to write what are the particular dimensions of all these variables. Let us suppose your eta efficiency is dimensionless, unitless quantity, so it will be dimensionless eta. What about rho? Obviously it will be your mass per meter cube, that means m L to the power minus 3. Here dynamic viscosity m L to the power minus 1 T to the power minus 1. Now come to angular velocity is 1 by T, and d to simple, d is a simple diameter, you can take this as L simply directly, and here q is L cube by T, or you can say meter cube per second. So it will be equal to L cube by T or L cube T to the power minus 1. So the number of pi terms will be what? Number of pi terms will be equal to n minus m, and that will be equal to 6 minus 3, that will be equal to 3. Okay. Now we know that we need to formulate 3 pi terms, okay, pi 1, pi 2 and pi 3. Okay. So when we'll convert, how we are going to convert this particular equation now can be written as f1 of pi 1, pi 2 and pi 3 equal to 0. Okay. So here I can write this equation in this particular form. Now I am going to understand how I can formulate pi 1, pi 2 and pi 3. So see, each pi term contain m plus 1 variable where m is equal to 3 and is also repeating variable. Okay. So every pi term that but in this particular case there are 3 pi terms. So just write pi 1, pi 2 and pi 3. Okay. Now we are going to select repeating variables. Okay. Repeating variables. So in that particular rule what we have followed yet, that we need to take the geometrical property first, then flow property, and the third one is fluid property. Okay. In this particular question also they have taken the first property as d, or you can say it as equal to a geometric property. Okay. They have taken the second variable as omega, this is obviously a flow property, and the third one is rho, which is fluid property. So they have this particular question has chosen this 3 repeating variable. Okay. And we have assigned exponent as a1, b1, c1. Okay. 3 variables, 3 repeating variables we have chosen. What are the next left? What is left now? Eta, mu and q. Okay. Write eta, mu and q in particular 3 equations one by one. Okay. So pi 1 will be equal to this equation, pi 2 this, and pi 3 this. Okay. Now the next step is simple. Just we need to find out how this pi term will function. So the first pi term is simple, was pi 1 equal to, because pi are actually dimensionless quantities. So when we are going to write the dimension of pi, so we'll simply put m to the power 0, l to the power 0, t to the power 0. And what is the dimension for diameter? L. What is the dimension for omega? We know, t to the power minus 1. And what is the dimension for rho? We know, this is m l to the power minus 3. So just we need to formulate equation for pi 1. We'll formulate in terms of dimensions. Okay. Here eta is also dimensionless. Now equate the powers of m, l and t. You will equate it, you will get c1 as 0, a1 as 0 and b1 as 0. Okay. So put all these exponents in particular equation of pi 1. What you will get? Pi 1 as simple equation eta. Okay. Now come to the second pi term. The second pi term says, obviously the equation was associated with term dynamic viscosity. Okay. You just need to write again all the dimension of all the variables. Pi 2 will be obviously m to the power 0, l to the power 0 and t to the power 0. And again write dimensions for d, omega, rho with their exponents. Okay. And finally write dimension for mu, m, l minus 1, t to the power minus 1. And you need to equate all the powers. Here you can see, when you are equating the powers of MLT, what you are going to get? C2s minus 1. Write equation for A2, that will be equal to 3C2 plus 1. Here C2 you can take from the equation 1, that is equal to minus 1, and you can solve it for A2 as minus 2. and power of t you can equate, and you will get b2 as minus 1. So now formulate equation for pi 2, that will come as d to the power minus 2 omega to the power minus 1 and rho to the power minus 1 multiplied by dynamic viscosity. So you will get as pi 2 as tau divided by d square omega rho. Okay. Now come to the last and third pi term. Okay. We have that equation as d to the power a3 omega to the power b3 rho to the power c3 and q. Write all the dimensions of all the parameters and equate the powers. What you will get? C3 as 0, A3 as minus 3 and B3 as minus 1. Put all the formulas on the particular equation of pi 3. What you will get? Pi 3 as q divided by d square omega. Okay. Now we need to assemble pi 1, pi 2, pi 3 in particular form. Okay. So how we can write? Substituting the value of pi 1, pi 2 and pi 3 in equation 2. Okay. You can write it as function of first pi term, second pi term and third pi term. Here we have formulated what is pi 1, pi 2 and pi 3. Just write it and equate it to 0. Okay. So this can be your final answer. If you want to extend it, just write eta equal to function of all left terms. This will be your final expression, or this will be your final answer. Okay. Now we are going towards the next question. Here the problem is 12.13. The frictional torque of a disc of diameter d rotating at a speed n in a fluid of viscosity mu and density rho in a turbulent flow is given by T equal to this particular equation. In this particular question, your final expression is given. You need to formulate, you need to prove that by using Buckingham pi theorem. Okay. Prove this method by method of dimension or method of Buckingham pi theorem. Okay. Now what is given? The number of variables involved here is T, D, N, mu and rho, obviously. So here the total number of variables will be what? 1, 2, 3, 4, 5. So n, so your n, the value of n is equal to 5. Okay. M is what? M is your 3. So number of pi terms will be what? Will be your n minus m, that is 5 minus 3. 5 minus 3 equal to 2. Okay. So number of pi terms will be equal to n minus m, 5 minus 3, that is equal to 2. Okay. Now obviously you need to formulate here only 2 pi terms. Okay. Again we have to take repeating variables in a particular manner, that you need to take the first geometric, then flow property, then third is fluid property. Okay. Here in this particular example the same manner has been followed. Pi 1, you can see pi 1, the first repeating variable is your diameter, the second repeating variable is your n, and third is your rho, and associated with term torque, or you can see T. Okay. The second pi 2 is d to the power a2, n to the power b2, rho to the power c2 and mu. Okay. And you need to remember how you are writing the exponents, a1, b1, c1, d1. Okay. That a1 series should be in pi 1, 2 series should be in pi 2. Okay. We need to formulate all this pi 1, pi 2, pi 3 in particular and correct manner. Okay. Now the dimension analysis of pi 1. Okay, we need to do the dimension analysis. We need to write all the correct dimension of all the parameters involved. Okay. So parameters involved for this pi 1, obviously it is dimension less parameters, so that will be equal to m0, l0 t to the power 0, and the other terms for diameter will be L, for n will be t to the power minus 1, For rho is m L to the power minus 3, and for T is m L2 T to the power minus 2. Okay. So, equate the powers of MLT, okay, and solve it. You will get C1 as minus 1, A1 as minus 5, and B1 as minus 2. Okay. Now, substitute the values of A1, B1, C1 in phi 1 equation. What you are going to get? Phi 1 as this term, T by D to the power 5 n square rho. Okay. Now, dimensional analysis, do the dimensional analysis of pi 2 the same way we have done for pi 1. Okay. Here, write all the dimensions of all the parameters. Okay. Apply the exponents, equate the powers of MLT, and then solve all the equations available now. So, you will get C2 as minus 1, A2 as minus 2, and B2 as minus 1. Again, solve it and put all the exponents value in pi 2 equation. What you are going to get? Pi 2 as rho divided by mu divided by d square n rho. Okay. So, we have derived equation for pi 1 and pi 2. Okay. We just need to assemble this pi 1 and pi 2 in particular function. Okay. And how now how we can write it? You can see function of f1 of this two, pi 1 and pi 2. We have formulated that. Okay. Or you can write it as, just take one function and take function of phi of another term. Okay. So, here you can write equation for t, that will be equal to like d to the power 5 n square rho phi, or function of phi, which includes mu by d square by n rho. So, this is how we can solve a particular equation that involves two pi terms. So, I am pretty much sure that you will be able to solve other questions by using your reference books, and the Buckingham pi theorem. Now it is clear to you that how you are going to take pi term, what is n, what is m, and what is a repeating variable, how you can select the repeating variables, in which manner. Okay. And if there are number of variables, how you are going to equate in a function. So, this is how this was how you can apply Buckingham pi theorem. The next topic in this particular chapter, the next topic is model investigation. Okay. So, what is this model in investigations? Or you can you know very well, whenever a big project is going to design, for an example, at think of a particular dam construction or about to start in a particular reach of a river. So, whenever the project of that particular dam with with head, with reservoir volume, whatever project or whatever design is that particular project is having, that is design. Okay. But we need to study that particular project, that particular dam construction in a smaller manner. We apply the same situation in a model, okay, of model of particular dam, and we apply the same conditions. Okay. And we check that particular project will work or not under safety considerations. Okay. That will be beneficial for us or not. So, there are many experimental investigations are involved with particular project, but that we do in a small or model form. Okay. So, in this situation, in this we need to go further with the analysis, with the experimental design. We do model investigation of particular prototype. So, the experimental investigations obviously are required to be carried out using tests with models of the actual machines or structures. Okay. Just we have take the example of dam structure. we need to do some experimental investigation before starting the project. Such investigations are essential for the problems which can not be solved with theoretical analysis. The small scale replica of the actual project or actual machine or actual structure is called model, while the actual machine or actual structure is called prototype. Okay. Let us suppose I am going to build a dam uh, across any river. So whatever the height of the particular dam we have designed, whatever the width of particular dam, what are the dimensions, so we need to convert that prototype into a smaller model form, and we need to perform some experimental investigations in that particular project, so that we can analyze the safety features are good or not, if that particular dam, if we hope that that particular dam do not get destroyed under the water pressure. So this kind of investigations uh, are need to be verified first. So we build model of that particular prototype and do analysis. Okay. So similarity between model and prototype we are going to discuss. See, whenever we build any model from prototype, see, we need to keep in mind that there should be some similarity between model and prototype. So what kind of similarities are there, how we are going to apply it by using different dimensionless numbers, so we are going to discuss in this particular chapter. Okay. So types of similarities, there are three types of similarities. The first is geometric, second is kinematic, and third is dynamic similarity. Now we'll go through one by one. Okay. The first is geometric similarity. What is geometric similarity? That exists between model and prototype if the ratios of corresponding length dimension in the model and prototype are equal. Okay. Geometric similarity, that means we need to equate all the corresponding length, or you can say the dimensions of model and prototype, that should be equal. If that are equal, then we will say that geometric similarity exists between model and prototype. Okay. So here you can see length scale ratio. Okay. What is length scale ratio? You can represent it by LR, that will be equal to LM by LP. Here you can see BM by BP and DM by DP. This is what? LM is what? BM is what? And DM is what? These are dimensions of model, or either you can say in length, in breadth, or in depth. Okay. What is this LP, BP and DP? Are again dimensions of prototype. So ratios of all this particular dimensions in a similar manner, that should be equal, and should be equal to particular length scale ratio. If this kind of similarity exists in between model and prototype, so we will say that the kinematic, the dynamic, the geometric similarity exists. Okay. So this was length scale ratio. Another term is your area scale ratio. Okay. Area scale ratio will be what? AM by AP. Write AM, the formula for area will be length into breadth. So LM BM divided by LP BP, or you can write it as LR multiplied by LR, or you can say LR square. So this will be your area scale ratio. Now the next is volume scale ratio. The volume scale ratio, here you can see volume is what? Length, breadth and depth. Okay. Write the formula, you will get volume scale ratio as LR to the power 3. So there are another similarity that can exist is kinematic similarity. that exist between model and prototype if the path of homologous particles are geometrically similar and ratios of velocity and accelerations of homologous points are equal. See, here we are need to talk about time scale ratio, velocity scale ratio, acceleration scale ratio, and discharge scale ratio. Okay. Go to the time scale ratio. Here you can find out the time scale ratio as Tm by Tp. What is your velocity scale ratio? You can formulate and get it as Lr by Tr, length ratio by time ratio. What is Ar? Ar is your Lr by Tr square. Okay. And what is your Qr? That will be equal to, you need to formulate what you will get, Lr cube by Tr. Okay. So this is for all the three types of similarities in which we have gone through the introduction of geometric similarity and kinematic similarity. The next part of this particular lecture will continue in another video. Okay. Thank you. Jai Hind everyone.